So we're going to continue our discussion of acids and bases and look at equilibrium situations with acids and bases, which are going to occur, of course, with our weak acids and weak bases, because those are the ones that are not completely dissociated. As you can see here, my original notes were not correct. Um, these are the acids, weak acids are, which are mostly not dissociated. Their equilibrium lies far to the left. So there are, of course, the 8 strong acids that you're supposed to memorize from that previous set of notes, but some acids that are sometimes we sometimes miss are our COOH, organic acids. If you see that in the formula, you know it's an acid, an organic one. And just like with this first one, acetic acid, which we've looked at before, it's that end hydrogen that comes off. That's the acidic hydrogen, and the one that pops off when we react those acids. Now, in general, when we have a series of acids, the more oxygens, the stronger the acid. And you can remember that by simply remember that HClO3 and H2SO4 are both strong acids, whereas the rest of them are not. A few textbooks will list HClO3, but AP generally does not. So those are strong acids. So anything with fewer oxygens are going to be not as strong. And the reason is the more oxygens there are, the weaker the bond is for the hydrogen with the rest of that molecule. And remember, a weak hydrogen on there, a weak bond to the hydrogen means it's going to pop off easily. That means it's a strong acid because it's the hydrogen ions floating around that make it strong. So the easier it is to pop off that hydrogen, the stronger the acid. Also, we have this situation, the stronger, more electronegative that element is with the OH bond, the stronger the acid is going to be because it pulls electrons away from that OH bond, and it's going to result in a weaker hydrogen attraction to that molecule, so it's going to pop off easily. So why is HF the only weak hydrohalic acid? The rest of them, HCl, Br, and HI are strong, is because this bond is strong. The HF bond is stronger. Fluorine is more electronegative. And if that bond is stronger, it's going to be harder to pull away the hydrogen. So think about it. If you don't get those hydrogens pulled away, then you're not going to have a strong acid. Must have those hydrogen ions floating around in order to have the acid be a stronger acid. Now, weak bases, we know that the strong bases are the ones that are hydroxides of groups 1A and 2A, except for magnesium. The rest of them are easy to recognize. They're all hydroxide compounds. It's the organic bases that we sometimes miss. We know NH3 is a base. I hope you know by now that it's a base, and it's going to produce hydroxide ions in water. The same thing happens with any organic base that has that NH2 on the end. These are just like kind of like derivatives of ammonia. So when we react to these in water, they're going to act as dirty, nasty hydrogen stealers just like ammonia does. So if we want to look at methylamine in water, methylamine is CH3NH2. And if you react that with water, again, dirty, nasty hydrogen stealer, it is a weak acid, so equilibrium arrows, we end up with CH3NH3 plus OH minus. So that's how we get our hydroxide ions. Now, what we want to look at now is how we calculate the strength of these weak acids and bases. How do we get the pH? Now, you know if we have a strong acid or base, the pH is fairly easy to find. It's just the it's just the negative log of the concentration of that acid. However, when we're dealing with a weak acid, the concentration of the acid itself is not the concentration of the hydrogen ions that are in solution. This is not a completion reaction type of situation. So we're going to have to use a Rice equation. So let's set that up. If we're dealing with acetic acid, we've got CH3COOH, and it's going to react and form. I'm doing the Arrhenius equation here. If it's, you can do either one, Arrhenius or Bronsted. You can include the water if you want to, but remember, water's a liquid, so it won't show up in the equilibrium expression anyway, so no problem leaving it out when you can. So CH3COO minus plus the H plus. We know that the initial concentration it gave us up in the problem is 1.00 times 10 to the minus fourth molar for our acetic acid. We have nothing at the beginning for either of the ions, but then we're going to dissociate some X amount of CH3OOH and increase both of these ions by that same molarity. So we end up with an equilibrium concentration of 1.00 times 10 to the negative fourth minus X, X, and X. So now we can write our equilibrium expression. We know that our Ka for the equilibrium expression for an acid, equilibrium constant for an acid, is equal to the concentration of CH3COO minus times the concentration of the hydrogen ion divided by the concentration of CH3COOH. And it gave us the Ka as 1.8 times 10 to the minus fifth. So 1.8 times 10 to the minus fifth is equal to, both of these are x, so x squared over 1.00 times 10 to the minus fourth minus x, which remember we can neglect any added or subtracted x, and we're going to end up with x squared over 1.00 times 10 to the minus fourth. That results in x squared. If we multiply those two terms, 1.8 times 10 to the minus fifth and 1 times 10 to the negative fourth, we end up with a value of 1.8 times 10 to the minus ninth. Now we'll need to square root that value. Don't forget to square root the value, and when we do, we come up with an x value equal to 4.24 times 10 to the minus fifth. That is molarity, and it's the molarity of, and the species that we care about up here in our Rice equation, because that's what we're going to determine pH from, is the hydrogen ion concentration. Always watch. Sometimes it's hydroxide ion concentration, and if you put down the wrong thing, you're going to do the wrong calculation for pH, so watch that. So this is the hydrogen ion concentration, and it's very tempting to box that and move on, but that is not what the problem asked for. The problem asked for pH. So now, recalling from our previous work that pH is equal to the negative log of that hydrogen ion concentration, the negative log of our 4.2 times 10 to the minus fifth, we get a value for our pH of 4. We need 2 sig figs, 3.7. So there's our pH for this solution. Let's look at another similar, well, first of all, let's look at how we determine the percent dissociation, because they often ask for this. It's the change divided by the initial concentration. Change is X. Okay, so to get the percent dissociation for this particular problem, we need to take the X value, which was 4.24 times 10 to the minus fifth, divide it by the initial concentration, which was 1.00 times 10 to the minus fourth, times 100, and we get a percent dissociation of 42.4%. Okay, so moving on. In our next problem, we have a situation where it says to calculate the OH minus and the pH. So we have to be careful about what we're actually getting for our final answer for a 15 molar solution of ammonia. And it gives us the Kb for ammonia. Kb because we're dealing with a base this time, not an acid. So once again, it's a weak base. So we're going to use the Rice equation. And the equation for ammonia, this time we have to use water. And the classic, we've done this many times in the past. This is the reaction for ammonia in water. Our initial concentration is going to be 15.0 molar for our NH3. Water is a liquid. Be careful. We do not care about what happens to water. So that's always going to get X'd out. 0 for both of these to begin with. And you'll write minus X plus X plus X so many times in acid-base equilibrium. You have to be careful because when you get back to a gas phase problem, then you'll have to be careful not to miss those 2x's and 3x's, etc. So be careful for that. So 15.0 minus x, x, and x. And now we can write our Kb, and that equilibrium expression is going to be NH4 plus times OH minus over the concentration of NH3. Kb, very coincidentally, it is totally a coincidence, for ammonia is the same as the Ka for acetic acid, but 1.8 times 10 to the minus fifth is going to be equal to x squared over 15 minus x, which is approximately equal to x squared over 15. So we get the value of x squared being equal to 1.8 times 10 to the minus fifth times our 15. Gives us a value of 2.70 times 10 to the minus fourth. X then is equal to 1.64 times 10 to the minus second, and that's a molarity. Now be careful because this time, what's that X equal to? It's equal to the hydroxide ion concentration. So that's hydroxide. It did ask for this, so this is a reportable answer. And it does, I could see argument for it being 1.6 because of the 1.8 sig fig, so let's go with 1.6. Times 10 to the negative second molar, OH minus. And then as far as the pH is concerned, be very careful. Don't take the negative log of the hydroxide ion concentration and call that pH. The negative log of the hydroxide ion concentration is POH. So POH is going to be the negative log of that 1.6 times 10 to the minus second. Which is 1.78. Don't box that. That is not what it's asking for. It's asking for pH. And remember, pH is going to be 14 minus the POH, which is 14 minus that 1.78, and we get 12.22 for our pH of this solution. Okay, one more type of problem that I want you to look at. And this is when they give us a certain molarity of an acid and they actually tell us the pH, and this time they're going to ultimately be asking us for the Ka for this particular acid. So it is switching it around a little bit, okay? Since it has a pH of 2.67, it gives us the pH of this solution, so we can take 10 to the negative 2.67 and that's going to be our hydrogen ion concentration. So our hydrogen ion concentration here ends up being 2.1 times 10 to the negative third molar. Okay, so that's our hydrogen ion concentration. And that's our very important thing to know. This is our equilibrium hydrogen ion concentration. That's very important because now we're going to do the Rice equation for this acid, and hydrocyanic acid, HCN, is going to partially dissociate into H plus and Cn minus. It told us that this was 0.15 molar, and it told us that the hydrogen ion concentration was 2.1 times 10 to the minus third. I'm going to go ahead and write that as 0.0021 for both of these. So keep this in mind too. These both started out as 0, minus x for the HCN, plus x, plus x. That means that this value, both of these values, are x, which means we can simply subtract 0.0021 from the 0.15 molar, and we now have that our equilibrium concentration of HCN is 0.148 molar. Important for us to know all three of these values because this time it does not give us the Ka, it asks us to find Ka. And Ka is going to be the concentration of H plus times the concentration of Cn minus divided by the concentration of HCN. So when they give us that pH and we have all of those values, we can simply fill them in. 0.0021 squared, because both of them, both the H and the Cn minus, are the same concentration, and then HCN is 0.148 molar, which gives us a value for Ka of 3.1 times 10 to the minus fifth. So that's a problem in which Ka is being determined.